Now let's have a look at the tools that go into the tool holders. The pictures on this slide show typical tool holders for different sizes of parts. The cone end fits into the machine and the cutting tool goes into the other end. The important thing to notice about these tool holders is the outside diameter, which we need to consider in order to avoid a clash between the machine and the part being made. The table on the right informs us that the outside diameter of the tool holder, D2, varies from 25mm to about 75mm. Remember that these tool holders are holding cutters of less than 10mm diameter, so we need to be careful that there won't be a clash as we approach the part with the tool. This means that designs with shrouded pockets or shrouded drillings are difficult to make. It's also worth noting that the tool holders are often hollow, enabling coolant to flow through the cutting tool if it's been designed for that. Here's a typical cutting tool, an end mill. It should be apparent that it can cut on the sides as well as on the end face. The flutes of the cutter are arranged so that the entire diameter under the cutter is swept, so no pips are left. Please notice that the length to diameter ratio is usually 3 to 4, which restricts how deep a pocket you can machine. We can see on this slide that there are plenty of different end mill types. I'll talk you through a few of them. The second down on the left is a ball end mill, which, as the name suggests, has a fully rounded end. This is useful for machining 3D surfaces, as well as pockets with large radiuses around the bottom of the periphery. Third down on the left is a corner radius end mill, which is flat on the bottom face, but has a radius at the junction between the side face and end face. Typically, milling tools have a tip radius of 0.5 mm or 1 mm. For very small diameters, less than 5 mm OD, you can also get a 0.2 mm tip. If you're designing a pocket and you're not sure which tool you might use, select a 10 mm diameter end mill with an 0.5 mm tip radius. Pretty much every machine shop will have one of these in the machine already. This means that the radius between the bottom of the pocket and the sides will be 0.5 mm. It also means that the corner radii of the pocket should be around 15 mm. Here you can see a boring bar. Note the diamond-shaped yellow tip insert, which can be flipped around when the first tip radius becomes blunt. It's mainly used on lathes, and the shape of the hole that it makes can be seen in the diagram on the left-hand side. For turning operations, these tips are widely available with tip radii of 0.2, 0.4, 0.8, 1 and 1.2 mm. Note that this is different to milling tools, which commonly use 0.5 mm tips. This means that pocket bottom radii should be different depending on whether they are milled or turned. The bottom left picture on this slide shows a groove in a piece of material, and this can be manufactured using grooving tips as shown on the right. It could also be machined with a small diameter end mill from the top face. Note that some of the grooving tools have changeable tips which are cheap to replace, whilst others, typically the smaller diameter tools, are made from solid through-hard steel. These tools are well suited to making long straight grooves or undercuts. There are a couple more tools that I'd like to show you. We'll come back to them after this advert. Coming back to this slide, we can see in the top half the kind of tool that's used to make an undercut, for example as a stress reliever at the bottom of a threaded hole. The tool is passed down the pilot hole and then rotated so as to form the undercut. From a design perspective, it's important to realise that the whole diameter of the tool must pass through the pilot hole, which means that the undercut can't be a massive offset from the centre line. On the bottom half of the slide, we can see a lollipop cutter, which has a ball shape and cuts on all surfaces. It's usually used for deburring operations, but it can also be used to create chamfer surfaces by interpolation machining. By now you have a good understanding of the types of tools that are making your parts and how to design for them. Let's now move on to section 3 to look at design considerations in our 3D models.